Okay, so the last time we started talking about resistance, that's unit 4.2.4, and that resistance, as the name implies, is the resistance to the motion of electrons or to the flow of charge in a conductor, right? Now, the reason why resistance happens, not something I covered the last time, right? And so resistance occurs due to the vibration of the particles of the conductor. And these hinder the flow of electron, right? A flow of charge, which is electricity. Okay.
Yep.
And so if we, sort of recall the kinetic particle theory from way back in unit 2, right? Even solids, which is the case of metals, right? They're vibrating. So they're not moving about all over the place. They are vibrating in position. And so when you have an electron that's trying to move through these guys and they're vibrating, it's sort of going to, let's say it's going to collide with the particle and it won't flow as fast as it could, right? Because it's going to bump into the particles that are vibrating. And so that in essence is resistance. And so again, call back to unit 2 when we talked about absolute temperature and absolute zero. Remember those terms?
Yes.
Right, which is minus 273 degrees centigrade, which is a theoretical value. It has not been achieved. It possibly not achievable at all, right? But that would be the temperature at which particles have zero energy, right? But at much higher temperatures than that, scientists have materials called superconductors. And so they have them at minus 23 degrees centigrade, which is, right, still like 250 degrees off, right? So I'd say not even close to absolute zero, right? Minus 23 degrees centigrade is something you can get in winters in many countries. And so what happens is, because the temperature is so low, right, the vibration of the particle of this conductor is so low that resistance is nearly zero or very low, right? In some cases, nearly zero, right? The temperature might be different, the material might be different, but when they cool it, right, that happens. And so what happens, why are the superconductors? Because, right, when electricity is passed through them once, right, the electricity can continue to flow indefinitely within the superconductor, within the wires of the superconductor, the circuit of the superconductor, right, for infinity. Again, right, if it's maintained at that temperature and nothing else goes wrong. Infinity. Yeah. So that's what resistance is, right? Does that help clear up the concept of resistance?
Yes.
Haran?
Yes.
Yes.
Yes, Sobia?
When you said that they vibrate, do they like vibrate in fixed positions,
Yeah,
right?
yeah. Solids, yes.
Okay.
We talked about Ohm's law, and we got the equation, right? R equals to V upon I, or you can move that around and get V equals to IR. So this is Ohm's, right, law. We will come across that, like the proper definition of Ohm's law today, right? Resistance given ohms, and the ohm is resistance of a conductor in which the current is 1 ampere when the voltage of 1 volt is applied across it. We did a few numericals, so those are resistors are components that provide resistance, right? We can have fixed resistors which have a fixed value. We can have variable resistors in which the value can be changed. If they affect the current, then they are called rheostats. If they affect the potential difference across a device, then they are potential dividers. Then we talked about resistance in a metal wire, and that obviously depends on the material of the wire, right? And the resistance increases with the length and increases as cross-sectional area decreases. So the thinner the wire is, the more resistance there's going to be, right? And so resistance is directly proportional to length and inversely proportional to area. So if you double the area, that halves the resistance, right? And that's where we left off, where you guys felt a bit confused. Hopefully that's not the case today. So let's do numericals. Let's do some questions, crunch some numbers. So here's a question. You have a copper wire of diameter 0.50 millimeter. Right? And a length of 1 kilometer. And the resistance is 84 ohms. So R equals to 84 ohms. And so what they're asking you to calculate is the resistance of a wire of the same material and diameter with a length of 500 meters. So halving the length. So R is unknown for, right, same material and same diameter, but the length is 500 meters. So this is 1,000 meters, right? So we're halving it. And so we know that resistance and length are directly proportional,
Yeah.
right? So the way they're going around solving this, they're going, okay, R1 equals to 84 ohms and L1 is 1,000 meters, right? R2 is unknown and L2 is 500 meters, right? And the diameter is the same, so that's not of concern to us.
Okay.
Right? And then they say, oh, R is proportional to length, directly proportional length, and inversely proportional to area. So that's how we write it, right?
Yeah.
And so this guy is constant. So again, not our concern. So the way we're going to solve this is we're going to do, since it's directly proportional, R2, oh, sorry, right? Yeah, actually I got that right. R2. So what we're going to get, why are we doing this? Since they're directly
But
proportional, huh?
are we cross multiplying them?
Are we what?
Cross multiplying them.
Uh, no, right?
Okay.
Is that supposed to be L2 or L1 in the division
Yeah,
sign?
L1, sorry. Right, so the reason we're doing this is because the ratio is supposed to come out the same, right? Because it's directly proportional, so R2 divided by R1 is going to have the same ratio, like the same value, not ratio, sorry, the same value as L2 because they're directly proportional. So when the length increases, the resistance increases by the same, like, what's the word I should use? To the same degree. Okay.
Okay.
So that means that if you double the length, you're also doubling,
The resist.
right? And if you half it, then you're also halving the resistance,
Yeah.
right? So this ratio, this value of, the ratio of R2 to R1 for both of these will end up being the same. And so, right, you want to find R2. So R2 equals to L2 over L1 into R1. And if I can fit it over here, that is 500 divided by 1000 into 84. And so,
If I'm not wrong, it would be 42.
yep. And I mean, that's something we could have done in our heads, right? Simply because we know that the length has been halved, and so the resistance will be half as well.
Yeah. Okay.
A stands for area.
Yes, cross-sectional area, right? And because it's circular, so that's pi r squared for the cross-sectional area, right? Pi is constant, and so what depends is the diameter, the r squared. Why is it looking like an A? Pi. Right, so pi is obviously a constant value, it's not changing. So what depends, what affects the area is the radius, and the radius is the same for both wires, and so again that is not playing a part in our calculation. Okay,
Okay.
does this make sense?
Yes.
Yes, Hara?
Yes.
Okay, let's do another.
Yay.
So you're supposed to calculate the resistance of a wire. Resistance is unknown, right? What do we have? We have, right, the same material of wire with a diameter of 1 millimeter and length of 1 kilometer, right? So this is carry on. This is like part B, right? This is part A. The same material, right? But this time, instead of changing the length, right? Length is 1,000 meters, so 1 kilometer, and the diameter is 1 millimeter. So they've doubled the diameter. And so we know the relationship, right? We knew that when the diameter was 0.5 millimeter, the resistance was, and the length was 1000 meters, the resistance was 84 ohms. We knew that, right?
Yeah.
Okay, so again, R, sorry, not equals to, but is directly proportional length and inversely proportional to the area. And so this guy is same. So it's not going to play a part, right?
Yeah.
And obviously this is D2 and D1 is 0.5, right? R1 is 84 ohms. So how are we going to go about doing this? Right, if R is the radius of the wire, and so we know that the cross-sectional area, as I mentioned, is pi r squared, right?
Yeah.
And so that would mean pi d over 2 squared, because d is diameter, right? So you want the radius,
Yeah.
right? Or what they're doing is to make it easier, right? Area equals to pi over 4 d squared. Does this make sense? Do you know what happened over here?
No.
Right, so you just do the square part, right? What's d upon 2 squared? D upon 2 squared is d squared over 4, right? Pi, why am I making it a? Pi into d squared over 4, right? And so you just like, because the 4 is being multiplied with the whole, like, is the denominator for the whole thing? This just sort of like wrote it a different way. Why are they writing it a different way? And they're like, oh, so whether it's d1 or d2, right?
It's the same thing.
Pi over 4 is the same,
Oh,
right? When it's the same, it's not going to affect our calculations. And so we can sort of like, yeah, okay, fine, we don't need you. We're just going to work with this.
okay.
Making sense?
Yeah.
Pi is a constant value, right? 3.14 or 22 over 7, or right? However you take it. 4 is
Yeah.
obviously a constant value. 4 is 4, right? So whatever calculation I'm doing, if I'm always putting in pi over 4 in it, right? It's always going to have the same effect. So if I'm going to put in pi over 4 d1 squared, and area 2 is pi over 4 d2 squared, right? I'm going to draw a comparison. What is the factor that's going to make a difference to the area? Is it the pi over 4 or the d1 and d2 squared?
It's the D1 and D2.
Right? So I can get rid of these. I'm like, okay, fine. You're not playing a role in this, right?
Yeah.
What's actually affecting the area is the square of
Mm,
the
diameter.
diameter.
Yeah.
Okay?
Yeah.
And so, right, we can write it this way again, doing a ratio. Area 2, area 1 over area 2 equals to d1 squared over d2 squared, right? Which is, right, what do we have? 0.50 squared.
So wait, are we finding the R here or are we finding the A here?
We are finding the resistance, but we'll get to it,
Okay.
right? And so this is going to give us a value of 0.25, right? So the ratio of difference between the initial diameter and the new diameter is 0.25,
Yep.
right?
Yeah.
Now, because it is inversely proportional, right? R2 over R1 equals to A1 over A2. Why is it the other way around? Because of inverse proportionality, right?
Yep.
And therefore, R2 equals to A1 over A2 into R1. Do we know this guy? We just
Yeah.
know, right? And so
Yeah.
that means it's 84 into 0.25, which will give us what? 21 ohms.
Uh. Yes. Yeah.
Did this make any sense?
Can you please explain this again?
Okay. So from part A, or just part B?
Like
Just
just
start.
part.
Just part B. Okay, so the situation we have is we've got the same material and we've got the same length of wire, but this time what we're doing is that we are doubling the cross-sectional area. So the diameter is double, right? And so that's obviously going to affect the resistance. Now, from what we know is the greater the cross-sectional area, the lesser the resistance, right? It's inversely proportional. And so we wrote it out over here. So let me get my highlighter. We wrote it out. Resistance is directly proportional to the length and inversely proportional to the area, right? The length is the same. So again, right, that's not a concern for us. All we need to look at is, right, the relation of resistance to area. Now, the first thing we did is to simplify our lives, right? We uh, found out the areas, the ratios of the area, right? What is
So
the,
we find the area first.
I mean, we could plug in all the values. We could do pi r square for d1 and d2 and get actual value, right? We could do that, right?
But like we could have used the value of length as well, no?
How, why length? The length is the same in this case, right? It was 1000 meter, 1 kilometer earlier, and it's still 1 kilometer. So how is that going to affect resistance?
Yeah.
Okay. We used the value of length in part A because the diameter was the same diameter. The length changed from 1 kilometer to half a kilometer or 500 meters. So that's why we did this,
Okay.
right? In that case, the cross-sectional area was constant. So we didn't concern ourselves with what A was because it was the same for both wires, right? But this time A has changed. So that is what our focus is on. And so it's obviously a wire, it's cylindrical, and so the cross-sectional area is a circle, so it's pi r squared, right? Radius is half of the diameter, so it's d upon 2 squared. And so we move that about, and the only reason we're doing this, making life simple. Oh, so the area is, a factor of the square of diameter. Pi upon 4 is, the same in both, as I mentioned. And so we're going to remove that from our calculations. And so what we're going to get, the ratio of the uh, areas, the initial area and the new area, is the ratio of the squared of their diameters, right? Which is this, which is getting you 0.25. Okay, so I found that.
Wasn't it 0.5 instead of 0.50? Or it's the same thing?
In terms of value, it's the same thing, but oh, you mean what I wrote over here?
Yeah.
Yeah, so I should make that 0.50 because that is how it's given in the question,
Okay.
right? And what this does is it makes it two significant figures. Remember significant figures from way back when?
Oh yeah.
Right, so writing it as 0.50 or 1.0 makes it two significant figures. And so what basically that tells me is that my answer should be in two significant figures.
Okay.
Okay,
Yeah.
now that I
It
have,
would be mentioned in the question.
huh?
Like it would be mentioned in the question that how many significant figures should be there.
Normally, your answer should be two to three significant figures. Otherwise, a
Okay.
guidance is that it should be at least the minimum number of significant figures given in the question for any value. Over here, they've given 1.0 or 0.50 or 84. So those are all two significant figures. 1000 is four significant figures. So what's the least number of significant figures value given in the question? That's two. And so your answer should be at least two significant figures.
That's the minimum, right?
Yeah.
Okay.
Okay. So we took a ratio of the two areas, right? Why did we do it this way? Because, right, if we wrote this out first, maybe it would have made more sense like we did over here, right? Because of direct proportionality, right? R2 and L2 are both coming in the numerators, R1 and L1 are both coming in denominators. In case of inverse proportionality, right, R2 is in the numerator, A2 is in the denominator, R1 is in the denominator, A1 is in the numerator. This is because of inverse proportionality. And so, right, what I'm concerned with obviously is R2. And that's why I wrote it this way. And so what I'm getting over here is A1 over A2. So if I've written this first, then I go back and do all of this, it will make more sense that, oh, I'm finding, instead of, doing lengthy calculations, I just made it easier, found that, oh, A1 over A2 is 0.25. And so I just multiply 84 by 0.25 and I get 21 ohms. And this is how you would approach a question, right? So in case you're asked to find resistance with changing length, or you are asked to find resistance with changing cross-sectional area. Okay.
Yep.
Okay. Now, moving on. Haram, you okay with that? Haram, you there?
Yeah,
Yeah, okay.
yeah.
All right. So if it's clear, that's good. Next up, we are going to talk about Ohm's law. Right? And what Ohm's law states that the current in a metallic conductor conductor is directly proportional to the potential difference across its ends if the temperature and other conditions are constant. Right? And what that gives us is V is directly proportional to I, right? And if we turn that into an equation, V equals to I R, right? So that is the constant over here for a particular metallic conductor, right? Not for everything. So in each scenario, for each conductor that we're talking about, right, resistance will be constant given whatever value of uh, voltage or current you have. So this is the constant of the right Ohm's law equation. And if we just go back, we are familiar with this equation because we got it over here. Remember this,
Yes.
right? So, right, if we shuffle this around, it looks more familiar to us. It's R equals to V over I, right? Or I equals to V over R,
Whatever is the subject for the
whatever is the
question, right?
subject, right? And so, right, that proportionality again tells us that V over I equals to a constant, which is in this case the resistance. And this is given that the temperature is the same and other factors that would affect resistance are also the same, right? They're not changing. So what's happening over here, just a sec. Huh. Just a sec. Okay. So remember at the start I told you that resistance is linked to temperature, and I mean in resistance is because of the vibration of the particles of the conductor. And so I talked about absolute zero, right? When it's cooler, the particles have less energy. Although we're not talking about absolute zero, we're talking about a much reasonable temperature, minus 23 for superconductors. Again, we're not talking about superconductors, but just to get the concept across. that at lower temperatures the energy of the particles is lower, so they're vibrating less, and so the resistance will be lower because they're not getting in the way of the movement of the electrons, right?
Yeah.
And so, right, if the temperature is kept constant, so what would happen if the temperature increases, right? If the temperature increases, the particle vibration will increase, right? And that would increase the resistance. Now, in a conductor that follows Ohm's law, right? This is, Ohm's law, this thing. So a conductor that follows Ohm's law, right? There are two things. V is directly proportional to I. So if you increase the voltage, you are increasing the current, right? And you always have the same resistance. But in case of an increase in temperature where the resistance is increasing, right? You take this, right? And you increase the voltage as well. And so you're going to get
So,
a constant current. Haram, are you saying something?
yeah. So like it would be better to understand if you could like explain it with an example.
With an example.
Yeah.
So any like metal wire, for example, right, that is like we normally come across when we are dealing with electrical appliances, those are ohmic conductors,
Yeah.
right? And so that means that an increase in voltage, right, would result in an increase in the current, given that the temperature and everything else is the same, right? So temperature is going to affect resistance. If it gets hot, if it gets hot, right, for reasons that I just explained, the resistance of that wire is going to go up, right?
Yeah.
Along with the increase in resistance, the voltage also increases. And so if you look at this equation, if voltage increases and resistance stays the same, that means you've got more current going through, which is not what we want, right?
Yeah.
And so when resistance increases along with the voltage, the current remains constant. Okay, so you're supplying the same current to whatever
Yeah.
device you've got plugged in, for example, a lamp, right? Or your mobile phone charging, right?
Yeah.
Okay.
Thank you.
Now, there are certain graphs given over here. I'll take you to the book. Might be better than working on the whiteboard in this case. So let me just put that up for you guys. Right, so here they're mentioning Ohm's law that's given over here. And so an ohmic or linear conductor is basically, right, as we know, as the voltage increases, the current will also increase. All right.
Yes.
And so what you're going to get is a linear graph. Then you got something called semiconductors, right? Oh, by the way, an ohmic conductor, the resistance does not change, But the resistance of an ohmic conductor therefore does not change when the potential difference does, because when the potential difference, the voltage is increasing, the resistance is increasing, right? R equals to V over I, both of them are increasing and resistance stays the same. In fact, let's move over here. A semiconductor, right? The graph looks like this. And so what's happening over here is this semiconducting material, this diode, what it does is you can see that the graph is going to the negative voltage side as well, right? But regardless of whatever the value of the voltage on the negative side, the negative voltage basically means that they're moving voltage in the other direction, right? So it's a change of direction of flow, but you're not getting any current out of it, which basically means that, right, a diode has a small resistance when connected one way, and you can see that as the voltage increases, right, the current is increasing, but it has a very large resistance when the potential difference is reversed. And so, right, if this was an ohmic conductor, then you would see the linear graph going the other way, that when a voltage is applied in the opposite direction, you're still going to get a current in the opposite direction, right? And so that's what the negative value would indicate, right? Negative value indicates the change in direction of flow of the current and the voltage. In this case, it's allowing current to flow in one direction, but not at all at the other, right? Regardless of whatever the value of voltage in the other direction is, there's no current. Okay. So this is what a semiconductor diode is like. And they've given that explanation over here. Then the explanation, for some reason, that explanation of heat and everything is missing from the IGCSE books. And so I'm referring to the O Level book, right? And they're mentioning that the metal, right, it carries, the current is carried by free electrons. And when the temperature increases, the atoms vibrate faster. It becomes more difficult for electrons to move through, right? And this means that the resistance of the metal has increased. And so in this case, right, if the resistance is increased, the potential difference across the conductor also increases if a constant current is to be maintained. That if, right, so whatever I explained on the whiteboard to you, that the current remains the same. So what, like if the resistance is going up, it's not that automatically the voltage increases. No, you need to increase the voltage as the resistance is going up and it's becoming hotter if you want a constant current to be supplied in the circuit. Otherwise, the current is not going to remain constant. Right? If this is a bit confusing at the moment, maybe like, give it time and review it after class, maybe after like a few hours, or, tomorrow before class, and we can review it again. And so maybe like, your mind would be able to sort of process
Process
that.
it.
Yeah, process it. I may have, maybe jumbled it up. I don't know if you felt that way in my explanation, but right. So the current will remain, like if you want to maintain the current when something's getting hotter and the resistance is increasing, then you would need to increase the potential difference to maintain the current, right? And so the effect of increasing resistance due to temperature can be seen in the curve for a filament lamp. And so filament lamp are those old lamps with the glass and the wire going through it, and they used to, like, light up yellow. If you've ever seen them or used them, I don't know. And so you can see over here, up to a certain point, they are behaving like an ohmic conductor, right? As the voltage is increasing, the current is increasing. Over here, it starts to curve, right? The resistance is increasing. Why? Because it's gotten hot. And so at that point, right, because the resistance is increasing, if you're increasing the voltage, there's not so much difference in the current as there was earlier. And so there will come a point where the current will become more or less constant when it gets hot enough, right? So it's getting hotter, you are increasing the voltage, and so the current is not changing as much. So it's not exactly the same, but the change is less drastic. And so at this point, it becomes non-ohmic, right? Meaning it's not following Ohm's law. right? Just like a semiconducting diode. On the reverse side, right, this part, it is non-ohmic, so it is not following Ohm's law that V and I are proportional, because you're increasing the value of V on the negative side and you're not getting any current, and so that is against Ohm's law, right? So the explanation for the filament lamp is given here. It is a non-ohmic conductor at high temperature. At high temperatures, at low temperatures, it is ohmic. For a filament lamp, the IV graph curve flattens as V and I increase, and that is the resistance increases as current increases and makes the filament hotter. Okay, so that's the only explanation they've given, and that's good enough for us. Okay, the resistance of a semiconductor. So the last thing we have over here is a semiconductor thermistor, right? Decreases if the temperature rises. So this is a different kind of material where the effect is opposite, right? Increasing temperature decreases the resistance, and so their graph is different from what you'd expect. In this case, right, you can see that changes in uh, voltage are producing larger changes in current, right? And the graph is sort of bending upwards. Can you notice that? As you
Yeah.
increase, as it's getting hotter, smaller changes in voltage are producing greater changes in current
Yeah.
instead of flattening out. And so an example of a thermistor is a light, like it's not an example of thermistor, but the thermistor is an example of uh, uh, a case where the resistance decreases with temperature. Another case is the variation of resistance with light intensity. So those are light dependent resistors. And in this case again, right, when the resistance decreases, right, in some of these materials, they're also semiconducting. So don't confuse them with the diode, right? The thermistor is also semiconducting. The light dependent resistance is also semiconducting, but just remember them by their name, right? So diode is like this, the thermistor, and the light dependent resistor, the LDR, is also like graph D over here. I've mentioned that obviously. And so as the intensity of light falling on it increases, the resistance decreases, and so the same kind of curve will be observed. Okay, and again, this is just stuff for you to know that this happens. So if a question pops up and they're like, oh, this kind of graph was observed, and you're like, okay, fine, so this kind of graph is, for example, right, it's getting hotter, and the current is not changing as much with the voltage, and so the resistance is high, and so that is similar to something that's happening with the filament lamp. Or it's like a diode, right? It's not allowing current to flow in the opposite direction. So basically that's what you need to sort of remember out of all of this. Okay.
Okay.
Gotcha. Now that brings us to the end of the topic of resistance. Next up is electric power, which is relatively simpler, right? And so we'll pick this up the next time, inshallah, right? So I'll see you guys in the next session.
Allah Hafiz.
Allah Hafiz.